Ship Canal Bridge behind me carries I-5 through the heart of Seattle, and thousands of cars cross the bridge every single day. How did the engineers that built this bridge over 50 years ago know how to construct it in order so the bridge doesn't fall under the weight, like I said, of thousands of cars? These things. Pretend there's one in my hand here, but there isn't actually one. They're called strain gauges. Essentially, they are a thin, flat-layered, snaking coil, essentially, of wire that is put into a plastic film that is attached to things in order to test for their strain, their elongation per unit length, when they're put under some sort of stress. That was a lot of engineering stuff I just said, and I don't know if that all made sense. So let me take you on a deeper dive into the equations that make this all make a little more sense. So an important equation that engineers use is Hooke's law. In one dimension, whether you're just lengthening or compressing something, it relates the stress, sigma, the force per unit area, applied onto something by using the Young's modulus E, which is basically a property that's unique to any material, and multiply that by the strain, epsilon, of the material, which is basically a ratio of when you apply a certain stress onto a material, how many units of length is it stretching per original unit length. When you make circuits, there's resistors, there's things that impede the flow of electricity, but then the wire itself, each material that you use in a circuit actually has its own small resistance. Usually it's negligible, you don't really factor it in when doing any calculations, but the wire actually has its own resistance. And how you determine that is by this equation. Essentially, the resistance is equal to the resistivity of a material that's used to make the wire times the wire's length. So the longer a wire is, the more resistance inside the wire that it'll have, divided by the cross-sectional area of the wire. In a strain gauge, when you bend something back and forth, the amount of material that makes the wire doesn't change. So basically, the material inside a wire has to spread itself out when you lengthen a piece of wire, and then push itself together when you put it into compression. And that is governed by Poisson's ratio. And essentially, that is what a strain gauge takes advantage of. When it's placed on a material that undergoes some stress and it bends. If you know how much the resistance side of the wire changes based on how much the cross-sectional area and the length of the wire changes, you can use physical laws to trace that change in resistance all the way back to a strain based on the change in length of the wire. And based on that, you can calculate the stress placed on some sort of block of concrete or really anything. And from there you can calculate how many cars it'll take to be put on this bridge until it falls. And make sure that doesn't happen. And make sure the bridge doesn't fall. So, as a mechanical engineering major, I first heard about this in my mechanics of materials class in the middle of sophomore year of college. And then I heard about this again in the electrical engineering class that I'm taking right now. And naturally, because I'm an engineering student and I learn things the hard way, I want to make a strain gauge of my own. And
the way I'm making this strain gauge is by putting it into a Wheatstone bridge, also consisting of 2 fixed resistors and a variable resistor. Between the first and second resistor in each pair, I stuck a voltmeter to measure the voltage output of the circuit. I'm using a potentiometer as a variable resistor. I can change its resistance value to calculate based on these equations, but in this video clip I'm just making sure my Wheatstone bridge actually works. I end up replacing one of the resistors in the breadboard here with leads to the ruler, which I'm using as a strain gauge based material. Instead of thin snaking wire, I used Bare Conductive's electric paint based off a video I saw by ForceTronics, which explored doing the same thing that I am, links in the description. Ideally, you can quote-unquote cold solder wires to the paint to make a strong connection, but the connection was unstable, and my voltage and resistance outputs were as well. I even went to a makerspace to try to normal solder the breadboard wires in the paint, but the solder just didn't stick. I started becoming frustrated. But then I had a breakthrough.
So, I'm looking at my circuit over here, let me connect this back again. Seriously being confuzzled about why, like, when I press, like, so this acts up again, right? I'm having a lot of trouble with actually, like, keeping this stuff in. But this resistance just keeps on going down, right? Sort of stabilizing right now, I think, but it was going down quite a bit. Anyway, this completes the circuit too. So, maybe I should have built this on like the back, because it's not metal, it's just cork. Cork doesn't finish the circuit, so you know, that might be a better decision.
Time for round 2. I applied electric paint onto a smaller section of the back of the ruler, but I still had trouble, including with contacts staying in place and getting voltage and resistance readings.
Yeah, it's just like normally connected, and I don't know why it won't, like, you know, just stop at one resistance. Like, it'd be great if I could.
Third time's a charm, huh? Back to the on-campus makerspace I go, with my usual equipment and a new ruler in tow. Same bark, same metal, same flexibility, but it's a shorter length and not already compromised by electric paint. I measured and cut out a stencil of a snaking wire pattern using a laser cutter, like I show here. Look at that thing go! While that was going, I cut and stripped some new wire and soldered it together with shorter lead wires on both sides, with one side of each superglued onto the cork. With the stencil cut out, the ruler was ready to get some electric paint slathered onto it, which is exactly what happened, with a few oopsies where the rows of paint bled together, which I fixed by grinding out the cork from underneath it.
Okay, might be dark in here. I've got the lines down because heatwave, AC, same Wholesome bridge, except now that I have two equivalent resistors here. I got a pot right there, and then I have two leads where I'm measuring out to the voltmeter. You can see this is what it looks like right now. And then, as I was showing you pictures before, I have this lead coming out right there. These two leads are basically like the fourth resistor in the Wholesome bridge, like the unknown resistor. Unknown resistance, excuse me. They come out to like this, they're soldered to like a thicker wire. This wire is like soldered over here. And then there's like this little lead that's like super glued onto the ruler, and then cold soldered with the paint onto this like snaking current sort of thing. And then same thing on the other end, it just goes out to the ground, goes back to the battery. So that's the circuit. And I'm going to try to figure out a way to test this right now as everything's connected. First good sign is that the voltage is unchanging. It's consistent at around 7 volts, and it wasn't doing any shenanigans like going up or down or anything when I was moving it. When I'm moving a little bit, all the contacts seem to stay pretty well in place, so that's also good. Now, if I try to move this over here, and then do some bending, this should change a little, and then it should go back. But it probably isn't because the paint is too flexible. If I do it the other direction, it also changes. And then it goes back down. Here we go, I think I figured it out. If I bend it inwards, there's not much change. But then, okay, I think the best way I can show this is if I do something like this. No, that's not it. Yeah, this thing is still a bit finicky, but you know what? When I bend it, the voltage changes, and when I don't, the voltage slowly stabilizes. Plus with the potentiometer in the circuit, I can calibrate this thing to oblivion to make sure that the voltage is 0 whenever it's not bent. So I'm pretty happy with this. Yeah, I'm gonna go frame this thing for a second. Boo! You suck! Give us some next steps! Okay, fine. There are 2 things that I want to do with this if I ever get a sliver of free time before I graduate college in 2 years. For one, I don't have enough hands to be able to bend this thing to get the voltage to change, and then look at the multimeter and write down the values, and then adequately track some sort of trend with the voltage changing as I bend it this way, or whatever other way. So I definitely want to find a way to be able to record forces automatically without me having to look at the multimeter every time that I want to do that. The ForceTronics video, that again I linked in the description for this video, used an Arduino system to do that. I've never touched an Arduino in my life. So, secondly, recording that all assumes that like the strain gauge output is perfect, but that's not necessarily true. In fact, sometimes strain gauges that are put into a Wholesome bridge, like you know how I put there are 4 resistors in the Wholesome bridge, and then I put one of them as a strain gauge. All 4 of them could have been the strain gauge. Like 4 separate rulers or whatever material that I have electric paint on, all acting as strain gauges independently, or all placed on the same material, just connected in different areas. That is usually done to offset any effects that might come from material properties changing in temperature on a different surface. Putting all 4 resistors in the bridge as variables on the same material just removes, I guess, variables from the voltage reading that you can get. But that wasn't necessarily feasible for me to do here as well. So if I were ever to redo this, I would do that as well. Making something that's usually made in an industrial scale like this as a DIY project is difficult, but it really helped me put together the physical quantities that are important to engineers and the electrical fundamentals that make those things happen. And those are strain gauges in a nutshell, and I hope you learned something from this video too. I'm not gonna go frame it.